the main points I'm going to make are that, first of all, individual differences are large. Second, that self-reports, asking people how good is your sense of direction, actually predicts that. Navigation abilities are sort of at least partially dissociated from what psychologists would traditionally have measured, or ways that they would have measured spatial ability, and that individual differences include strategy differences. And then I'll just sort of throw out some questions for what the implications of this might be for human building interaction. So I just want to start by talking about a study that was run by a couple of my colleagues, Colin and Dan Montello. And they were actually, what they were really interested in was how people's knowledge of environments changes as they get more experience of an environment. So what they did was they brought people they drove them through 2 routes through a very sort of exclusive neighborhood of Santa Barbara, which is very wooded and has very windy roads. And one of them was this path here, what they call the S route. The other one was what they call the U route. And what they did was they brought the subjects there, and they would drive on these 2 routes every day, 1 day a week for 10 weeks. And they were also interested in how people, when they learn the layout, and they learn a couple of places, how they might integrate that information into one representation. So on day 4, they also drove them from one of the routes to the other. And the other one, they got to experience the relationship between the 2 routes. The previous days, they had been blindfolded when they were going from one route to another. And they pointed some landmarks along the way, and then they tested their knowledge of the environment each week. And so one of the main ways we test knowledge is we just put people at each landmark and ask them to point to the other landmark, and that gives you a sense of, do they have this metric knowledge of where that landmark is in space. So as I said, what they thought was going to happen was people would gradually get better, and they would get better at different rates. But in fact, that's not what happened. What they found was that there were these enormous individual differences. So there was this guy here who, when you asked him to point the first day, he was really accurate. I mean, the very first day, he was very accurate at pointing to where landmarks were on the route. And like on day, this is when he experienced the relationship between the 2 routes. Again, he was really accurate. I mean, if you're pointing randomly, the chance would be 90 degrees, and this guy was, down at about 30 degrees on the first day, so he was really good, and, obviously it was always good. Then there were people that, basically they were at chance, and they stayed at chance. They just never learned the layout of the space at all. And then there were some people who kind of learned, and some showed a small improvement, and some showed a large improvement, but the individual differences were much greater than any sort of learning trends that they saw. So this effect is, this research has now also been replicated. People walking on a college campus rather than being driven, and also in a virtual environment. And there's an experiment now called Sultan, where you learn this virtual environment, and you can learn separate places and integrate them, and it's available to researchers if they want to get sort of a measure of how good people are at this. And again, what this has shown is that some people are good at learning the individual routes, but they can't integrate them. Some people, can't even learn the individual routes, and some people are really good. They can learn the information from the individual routes and integrate it. And just to show, again, I think this is really compelling of the differences that was found in Ishikawa and Montello's work. This is the actual 2 routes that they learned and the landmarks on them, and they had to also draw a map every time. And this at the end, this is how this really good person, this is the map they drew of the space, and you can see it's almost perfectly accurate, whereas these are much poorer maps. And like this guy, all he did was there's 2 routes and they're connected, right? That's all that they got even after 10 weeks of being of this. So one thing is that this ability to sort of form an accurate spatial representation from route experience like this, there's huge individual differences. So the next point I wanted to make is that that self-reports are pretty valid. So how many people think they have a good sense of direction? And how many people think they have a bad sense of direction? You're probably right. So we seem to know how good or bad we are, and we're willing to admit it. So this was first shown in a study by Kozlowski and Bryant. But one of the things we did in Santa Barbara is we created this scale called the Santa Barbara Sense of Direction Scale, which is basically you answer 15 questions. You know, I don't have a very good mental map of my environment. I'm good at, good at giving directions, etc. And so this has actually been used a lot. It's been used in a lot of studies now, and it does seem to predict people's ability to navigate. So things like if you just ask people to point to landmarks in a known environment, you know, if you're from USC and I asked you to point to places at USC, this would predict how well you could do that. Your ability to point back to where you started after blindfold walking, your ability to point to landmarks in a newly learned environment that you've just learned, and your accuracy in judging the direction. This was an interesting study where people were shown pictures of, they were oriented to their campus, shown pictures of the campus, and they had to turn their body to what direction they would be facing in the environment if they were seeing that picture. And that was correlated really highly with this sensitive. So those are just some examples of things it's correlated with. So it's turned out to be a useful questionnaire because it gives you it's a way of just at least getting a quick idea of whether somebody's going to be a good navigator or not. The third point I wanted to make is that navigation ability is not necessarily the same thing as traditional measures of spatial ability. So the classic task used to measure spatial ability is mental rotation. You see an object here, and you have to say which of these objects here could be this one rotated in space. This is another test called the embedded figures, where you have to sort of look at each of these shapes on top and sort of trace where they would be in these more complex figures down below. And this is a test that measures spatial working memory, or how much mental capacity you have for spatial things. And basically what happens is things appear in these boxes, and you start, maybe you see a series of 3, and you can do that, and then you go up to 4, and you can do that, and sometimes at some point when you get up to a sequence of 5 or 6 things, people break down, and that gives you a measure of their capacity. So we did a study where we measured people's spatial abilities as they would traditionally be measured in psychology. And then we also had them learn the layout of different spaces. There was a building that they learned by walking through the building, and it was 2 floors of the building. There was another building that they learned by just watching a video that's of somebody that somebody took walking through the building, kind of like the video that Liz showed us yesterday. And there was one where they navigated a virtual environment. And in each case, they just navigated this from a first-person perspective. This is showing you the maps of the buildings. And so our question was, do these sort of traditional measures of spatial ability, like mental rotation, do they measure are the people who are good at those also good at navigation, or are they completely separate people? Is it this sort of dissociation model, or is there some overlap, or maybe there's some mediating variable that is connected to both of them? So real quickly, the first thing we found was that we kind of had to separate the ability to learn a building that you really walk through from a building that you learn just by watching a video or using a desktop virtual environment. And another thing we found was that the correlations weren't very high, so I just wanted to highlight this one. Mental rotation, as I say, which is a very classic task used to study spatial ability, and it wasn't very highly correlated with your ability to learn a building from really walking through it. I mean, these are pretty low. And this is the sort of structured equation model we ended up with. Basically, these are latent variables that are, and the main gist I want you to get out of this is that these sort of traditional measures of what we call small-scale spatial ability were certainly, partly this latent variable partly correlated with ability to learn from direct experience, but it was more highly correlated if you learned from vision alone. And sense of direction was more highly correlated with learning by really walking than by vision, than learning from vision alone. So we sort of ended up concluding that there's sort of this partial dissociation between sort of your ability to learn a space and your sort of spatial ability as measured by these psychometric tests. And one thing that seems to be important and maybe different about learning a real space is the ability to sort of learn from updating your body position. So the last thing I want to talk about, which is kind of what our lab is working on a lot right now is individual differences in strategy, in navigation strategy. And so there was information in the literature, just again from asking people from self-reports how they navigate. Carol Lawton did some important research on this. She said, well, think of a recent trip you took and think about how you navigated. And some people said, I kept track of the direction in terms of north, south, east, west, or the relationship between where I was and the center of town. Whereas other people said, I figured out a route and I knew I had to turn right at the church and turn left at the park and things like that. So they just had a route. And there were sex differences, so that men reported more of these orientation strategies, keeping track of north, south, east, or west, or maybe salient landmarks and things, whereas women were more likely to say they followed routes. So, so we were interested in whether this is really true, because this was, again, only self-report. And we used a task which was developed by Marchetti et al. Called the dual solution paradigm. And basically what happens here is you take a walk through a virtual environment. This is just showing you the route that's taken in the virtual environment, but it's a first-person view. You're seeing a first-person view of the environment. And then after you've seen that, you are put somewhere in the environment and you're asked to navigate to another place in the environment. And so basically one thing you can do is you can take the route that you learned, but you can also, another thing you can do is take a shortcut. So, and then you can compute this, what's called the solution index, which is the number of shortcuts you took versus over the number of times that you navigated by either a shortcut or a learned route. This is all coming up automatically for me, but anyway. And so basically, what you see is there's a big range. Oh, this is automatically advancing. I don't know how to stop it. Let's go back. Okay, there. So some people, this is sort of shows the distribution. Some people always take the learned route. Some people always take shortcuts, but most people are somewhere in the middle. Okay. So so we wanted to study this in our lab to see how this is related. So this is all work done with my grad student Alex Boone, really done by Alex Boone. And so we created the same type of virtual maze. This is what ours looked like. And we taught people a route. They walk through this route 5 times. They navigate through this route. It's in a desktop environment 5 times. And this is what it looks like. There's arrows on the ground that's telling them where to go. And we actually found that people did more than shortcuts and learned routes. So here is somebody who basically took a shortcut to the goal. Here's somebody who took the path they learned. But then we also found that sometimes people reversed the learned route, and sometimes they just kind of wandered and got there eventually. Interestingly, there were sex differences, as you might expect from the self-report. And these are really shown nicely in these heat maps here of, this was like basically about 20 men and 20 women doing a bunch of these trials, and what you can see is that the men are much more likely to go through the center here, which is the shortcut, the route, whereas women are much more likely to follow the learned route. So that did come out, and in 2 different experiments, that the men were more likely to take the shortcut than the learned route. But that got us thinking then, of like, well, why would that be true? Why might, what's going on here? Not just in terms of the sex difference, but in terms of the individual differences. So is it that, the people who are taking the shortcut, the people that are taking the learned route, is it that they just don't have enough the spatial knowledge to be able to take a shortcut? Again, we're not really claiming that they have perfectly accurate cognitive maps, but they need something more. You need to know more than just the route in order to take a shortcut, right? So we said, well, why don't you tell them to take a shortcut? So we did a study where we just had people do the normal task. We just said, go to this place. They did a bunch of trials like that, and then they learn a new environment, and this time we say, take the shortcut to this place. And people did take a lot more shortcuts when you told them to. But you see the men were still taking more shortcuts than the women. But there was sort of a confound here because they had to do the shortcut always came second, so it could be that they were also learning. So we ran another study where one group were just told to navigate twice, and they Actually, the men did take more shortcuts on the second thing here, but whereas this group were just told both times to take the shortcut, and you can see they're taking more shortcuts. So what this is saying is like, well, if somebody takes the learned route, it doesn't necessarily mean they can take a shortcut, because if you tell them to take a shortcut, they're more likely to do so. So there was other things going on here, and this is one of the things we're interested in. Real quickly, I just wanted to give you, Alex just defended his dissertation last week, and he had this, I can't go into the details, but he made this really nice prediction that under stress, people would be more likely to actually fall back on learned routes because stress activates the hormone cortisol that's released in stress, activates or is connected. It affects the hippocampus, which might mean that you'll be less likely to access your knowledge. So he did some really nice studies where he really stressed people out. He made them put their feet in freezing water for a minute and a half. He made them give a speech to a bunch of students who were looking at them very sternly, and while they also had, eye tracking and ERPs and everything on them. He really stressed these people out. But the bad news for Alex is his hypothesis was not supported, and people basically did not change their navigation strategy under stress. But that's kind of a good news for humanity, because it means that in an emergency situation, maybe we still do have access to our cognitive map. So some current things we're doing right now. A lot of this is with Carol Huff, my current grad student. All of this work was done in desktop VR, so people weren't really navigating, and maybe when you're in the real world and there's really some energy differences to take, to how much energy you have to expand to take the shortcut versus the learned route, things might be different. So we're doing this in walking VR, and also hoping to do it in a real environment. We're also looking at trial effects. Most people take the shortcut some of the time and the learned route some of the time. So we're looking at things like, well, how much savings is there from the shortcut actually? And people are more likely to take the shortcut when there's more savings, when the difference between the shortcut and the learned route is greater. And so, and there may be time, and you have to think about the trade-off between the mental effort of figuring out the shortcut versus the physical effort of taking it. So there may be times when, if the shortcut is not that much shorter, you don't take the mental effort, and that might be adaptive. So more generally, we're interested in why it might be adaptive to sometimes take the learned route. So then, I guess the implications for human building interaction is we can't assume that everybody can or will navigate similarly. So can smart buildings, do they need to be detecting? Maybe, can they direct people to navigate efficiently? Like, on the airline where they say lighted things will direct you to the exit. Is this something that we need? Or does one approach fit all? Do we want buildings to be able to detect different types of navigators? And also, one of the things I've been interested in too is just whether obviously a big issue in this meeting is whether building design can affect